Over the summer, while I was an intern at the Aerospace Corporation, I got to take part in a project that pushed my engineering, problem-solving, and teamwork skills. The work demanded hours of my day and consumed my imagination. The team was described by a longtime employee as a group of people trying to build their way out of a prison cell. This is the story of the glider. Let's back up. In mid-July, I got an email from my project manager asking that I participate in what he was calling the Magic Carpet Glider. The goal was to build an autonomously navigating soft robotic glider out of Aerospace Corporation's AFC circuit technology that could, once launched 1,000 feet in the air, navigate back to the landing site by reshaping itself. We had 3 weeks. The challenge was, of course, impossible. Obviously, I was in. I was drawn in by the wide open space to test ideas, push myself, and see a project through from start to finish. Even more exciting, proving that this technology worked would mean that it could be used for applications like firefighting, where dropping 30 sheets of self-navigating plastic from a plane out to take measurements or release fire suppressants could be invaluable. So, to start, AFC stands for Autodynamic Flexible Circuit. It's exactly what it sounds like, a kept-on circuit that is able to flex under its own power. The idea is valuable for space applications because these little arms have very low size, weight, and power requirements. They're also very cheap to manufacture, and because they don't have traditional joints, are flexible. So how exactly do they work? AFC circuits work on the principle of CTE mismatch, when two materials expand differently in response to heat. If you take a sheet of Kapton and lace it with shape memory alloy wire, then run a current through the wire will heat up and shrink more than the Kapton. This pulls on the Kapton like a muscle and forces it to bend around the wire. Thus, you are able to electronically actuate your circuit. If you can change the shape of an object in flight, then you can change its aerodynamic properties and thus change how forces act on it. Theoretically, if your object is a glider, you can use this to steer. Our approach was hands-on and rapid-fire. We started with paper, folding and cutting designs that would be geometrically simple to actuate, and then considering how they might fare being tossed out of a rocket 1,000 feet in the air. Quickly, we realized that a traditional plane-style design would be lost without a starting velocity that we couldn't provide. We turned to drone-style flight, designing a glider that could move omnidirectionally based on inputs from the GPS. By curling up one edge of the flat glider surface, we could make the glider fall in that direction. Once we had a few paper prototypes, we went to the nearest parking garage and tossed them off to see how they behaved. Our first test was disappointing as we watched prototype after prototype plummet like sad rocks or catch a breeze and go flying. Back to the drawing board. We increased surface area and came up with new ideas for actuation. Instead of dropping them flat, what if we pulled up 4 sides to counteract yaw? It worked. With a better idea of dimensions, we sized our glider based on the weight-to-surface area ratio of successful drops. Then we started cutting gliders out of PEI, a heat-resistant plastic with similar properties to Kapton. I was the mechanical lead on the project, so I designed countless versions with cutouts to save weight, altering the whole patterns and the dimensions. It was a trial by fire of design for manufacturing and design for assembly. The glider needed to roll up into an 8-inch tube just to fit into the rocket for launch, so it needed to be flexible. On the day of launch, we were still only mostly assembled and had to solder components together in the Mojave Desert. We were under significant time pressure. Our launch window was only so long. In addition, the heat affected all our stuff, snapping wires, drying epoxy, and overheating laptops. Finally, we made all of our repairs and loaded it into the rocket. The countdown began, and we watched from a bunker as the rocket lifted into the air, the glider popped out, and floated off in the wind. Unfortunately, in all the rush of assembly, the only code uploaded to the computer was the default Arduino Blink code. After it deployed, we watched the glider sail aimlessly through the air and drift out of sight. As I said before, the project was impossible. Our project manager later told us that he fully expected us to fail. But by refusing to accept that until the end, we made incredible progress that can be built on by the next team of interns. The mechanical and electrical systems worked perfectly under extreme temperature, and all that remains is software validation. The glider project taught me to be a better engineer, but also that pursuing an impossible project is always worth it. I plan to bring the same perseverance to the Brooke Owens Fellowship.